Okay, so here's what we're doing today. This is about the problem that was on some people's tests that I felt bad about because I suggested the wrong method. Well, not the wrong method, so to speak, but it's a more difficult method. I should have said the shell method, but anyway, this is about the volume of a solid generated by revolving a region bounded by some curves around a line. And like I said on the test, I suggested the washer method, but it's easier if you use the shell method. So my punishment for myself for making that mistake, because I do feel bad about it, my punishment for myself is that I am going to show how to use the washer method. In the end of the day, it's really not that bad. It's just not what I meant to say. I meant to suggest the easier way, which is the shell method. But let's see how this goes, because it can be a good exercise. So I've got my region bounded by two curves, and I'm going to want to know points of intersection, so that's a good place to start. So set this equal to this. Get everything over to one side, and I made this so it's not too bad. So I've got that. So x equals 3 and negative 1. And let's actually draw a little picture here. Picture should not really be necessary, but it can be helpful, especially because we're doing this the hard way. I know what these curves look like. This is your classic parabola, y equals x squared, and this is a line, so we know how to graph lines. To draw an accurate picture, let me find the actual points of intersection, so maybe I'm not ready to draw yet. Let me find coordinates. So I know the x coordinates. I've got a point with an x coordinate of 3 and a point with an x coordinate of negative 1. To figure out the y coordinates, I should be able to plug it into either of these and get the same answer. So this should give me 9. And if I plug in negative 1 here, this should give me 1. So apparently I have to go up to 9 for this, but that's fine. So I've got a point of intersection up there, and a point of intersection around there. And one of my curves is just a straight line, so I'm just going to connect the dots. That's easy enough. And my other curve is just a parabola, and I know what this looks like, and I have these 2 points to guide me. So it looks like this is my region. I don't want to shade it because I always regret it when I shade it. And of course, I am revolving it around the line x equals negative 2. So maybe I'll draw that in red because it'll look nicer. And there's my spinny arrow indicating that I'm revolving it around that line. Right, okay. So since I drew that picture, you can sort of see why I would want to use the shell method. The shell method is where I take my slice parallel to the axis, and the axis is vertical. If I take a vertical slice, which is ultimately not what we're going to do, but I'm just explaining why it's easier, what makes it easier is I always have this line on the top and always the parabola on the bottom. No matter where I draw my vertical line, I have to imagine sweeping from left to right, but no matter where I draw it, it's always this line on top, this parabola on bottom. We're going to do this the hard way. We're going to use the washer method. For the washer method, I take a slice perpendicular to my axis, so it's going to be horizontal. What makes this difficult, fundamentally, just off of the picture is, if I draw my horizontal line near the bottom, then I'm going to want to know which curve is bounding me to the left and which curve is bounding me to the right. And if I'm drawing a horizontal line near the bottom, it's the parabola on both sides. It's like the left part of the parabola is my left side and the right part of the parabola is my right side. But if I move higher up and draw, say, a horizontal slice maybe up here, then I've got the line on the left and the parabola on the right, which makes things awkward. In the end of the day, this isn't that bad. I'm just going to have to break this up into two integrals. So, here we go. First, maybe I should write this down. This is basically how I remember the washer method. And this is going to be an integral with respect to y, because I'm taking horizontal slices and y tells me how high or how low to go. So, let's see if I'm ready to start this. Like I said, we're going to have to break this up into two integrals. There's the part near the bottom where I've got the parabola on the left and the right. So let's talk about that part first. There's going to be an integral just for that part. This is an integral with respect to y, so I'm going to put limits of integration that make sense for y. So the very bottom of the parabola has a y-coordinate of 0, and I'm going to go up to where the line crosses the parabola. That's my breaking point, which has a y-coordinate of 1. So we're there. Now, I want to do big R squared minus little r squared. Big R is the distance from the axis of revolution to the far end of my slice, like I'm imagining a horizontal slice. So the far end is the right side. So this is a horizontal distance. It's the distance from x equals -2 to whatever this x coordinate is. So this is a point on the parabola. The parabola has this equation, but I want to know the x coordinate. So I'm going to write x equals plus or minus square root of y. And the plus or minus is important here. The parabola does have a left side and a right side. If I take the positive square root of y, that's giving me the right side of the parabola. If I take the negative square root of y, that's the left side. So once again, what are we doing? I want to do big R squared. Big R squared, it's the horizontal distance from the right side of the parabola, which is the positive square root of y, and then I'm going to subtract the x coordinate of the axis, which is -2. So there we go. That's my big R squared. Little r squared. Little r is the distance from the axis of revolution to the near end of my slice, and I'm imagining a horizontal slice down here near the bottom. So the near end is the left side of the parabola. So I'm going to go the x coordinate for the left side minus the x coordinate of the axis of revolution. Okay. What I've written so far is, well, if I cut my region off at y equals 1, so I'm just doing this part near the very bottom, like up to where the line crosses, it's the volume generated by just that part. And so now I'm going to do the part starting at y equals 1 and going all the way up to the top. So let's do that. So plus, so now I have another little washer method. y is now going to start at 1 and go up to the y coordinate of this point, which we figured out somewhere. That's 9. Okay, now I'm going to have, well, something squared minus something else squared. So what's my big R? My big R is the distance from the axis of revolution to the far end of my slice, and I'm imagining like a horizontal slice maybe around here. And so the far end is still, here it's still just the right side of the parabola. So actually big R is going to be the same as it was. But now little r is going to be the distance from the near end, and now the near end, at least, I mean, when I say near, I mean near to the axis of revolution. So it's the line. It's the x coordinate of the line. So actually, it just occurs to me, well, we didn't need it before, but we need it now. I need the x coordinate of the line. So I just solve for x real quick. So little r is going to be that x coordinate minus -2. And that's it. I mean, in the end, it's not the worst thing in the world. It's just a bit harder than I meant. And by the way, this is set up but do not evaluate, so we can just put a box around this. We don't even need to simplify the really obvious stuff, like, of course, minus -2 is +2, but we don't even need to do that. When I say set up but do not evaluate, I mean you can really just leave it exactly like this. Of course, it's not impossible to evaluate. You could square these things out and do the algebra. It would be a bit tedious, but not impossible. But luckily, we don't need to do that.